The topic of the video is data centers, computational fluid dynamics, CFD, and fire management, leveraging third-party data centers for advanced fire modeling, real-time analysis, and intelligent fire risk management. Computational fluid dynamics in fire engineering. Computational fluid dynamics, CFD, is the numerical analysis of fluid flow, heat transfer, combustion, smoke transport, and associated physical phenomena using mathematical equations and computer simulations. CFD fire models solve the fundamental conservation equations: conservation of mass, conservation of momentum, conservation of energy, species transport equations, turbulence equations, radiation heat transfer equations, combustion equations. Common governing equations include Navier-Stokes equations, continuity equation, momentum equation, energy equation. Applications of CFD in fire modeling and management. CFD has become indispensable in modern fire engineering. Major applications include building fire safety, smoke movement prediction, fire growth analysis, flashover prediction, occupant tenability assessment, evacuation analysis, structural fire analysis, industrial fire safety, chemical plant fire modeling, oil and gas facility fire analysis, hydrogen fire simulations, LNG explosion modeling, battery thermal runaway studies, infrastructure fire engineering, tunnel fire simulations, underground station fire analysis, airport terminal fire safety, railway station smoke management, wildfire management, bushfire spread prediction, fire behavior modeling, emergency planning, resource allocation, data center fire safety, hot aisle, cold aisle airflow, smoke propagation, fire suppression optimization. Thermal management. Why CFD simulations require massive computing resources. High-fidelity CFD simulations are computationally intensive. A realistic fire simulation may involve parameter typical size grid cells, 10 million 500 million simulation duration hours to days, time steps, millions data generated, TB scale CPU cores required hundreds to thousands. For example, a large tunnel fire simulation using Fire Dynamics Simulator (FDS). Open foam, ANSYS Fluent, Star CCM+, Fire foam may require 512 CPU cores, 2 TB RAM, 72 hours runtime. Such resources are often unavailable locally. Role of third-party data centers. Third-party data centers provide scalable high-performance computing (HPC) resources through cloud platforms. Examples include public cloud data centers, private cloud providers, research supercomputing centers. Commercial HPC service providers uses remotely access computational resources via the Internet. The workflow is local user right pointing arrow, secure network right pointing arrow, third-party data center right pointing arrow, HPC cluster right pointing arrow, simulation right pointing arrow, results storage right pointing arrow, visualization, architecture of cloud-based CFD fire modeling. Stage 1. Data collection. Input data may originate from building information models, BIM, CAD drawings, laser scanning, IoT sensors, weather systems, historical fire databases. Examples: building geometry, material properties, fuel characteristics, ventilation configurations. Stage 2. Data upload. Data are securely uploaded to cloud storage. Typical technologies include object storage, distributed file systems, data lakes. Examples: Amazon S3, Azure Blob Storage, Google Cloud Storage. Stage 3. Mesh generation. CFD domains are discretized into millions of cells. Meshing processes are often automated in cloud environments. Adaptive mesh refinement techniques dynamically refine regions around flames, smoke layers, critical escape routes. Stage 4. Parallel computation simulations execute on HPC clusters. Typical infrastructure: thousands of CPU cores, GPU accelerators, InfiniBand networks, petabyte storage systems, parallel algorithms, domain decomposition, MPI parallelization, GPU acceleration, hybrid CPU-GPU computing. Stage 5. Post-processing. Cloud systems automatically generate temperature contours, smoke visualizations, velocity vectors, radiation maps, evacuation risk maps. Results may be streamed in real time. Real-time fire analysis using third-party data centers. One of the most transformative developments is real-time fire management. Real-time architecture. IoT sensors right pointing arrow, edge computing right pointing arrow, cloud data center right pointing arrow, AI models right pointing arrow, CFD digital twin right pointing arrow. Decision support. Sensor inputs include temperature sensors, smoke detectors, gas sensors, CCTV cameras, thermal cameras, occupancy sensors. Cloud-based CFD digital twins continuously update simulations. Examples: during a fire in a large shopping center, 1. Sensors detect smoke. 2. Data are transmitted to the cloud. 3. Cloud CFD predicts smoke spread. 4. AI estimates evacuation risks. 5. Emergency routes are dynamically updated. 6. Firefighters receive live recommendations. This capability can save lives. Integration with artificial intelligence. Modern fire management increasingly combines CFD with AI. AI applications include surrogate modeling. Machine learning replaces expensive CFD calculations. Benefits: simulation speed increased by thousands of times. Near real-time prediction. Algorithms: deep neural networks, physics-informed neural networks, Gaussian processors, transformer models, AI-based fire prediction. AI predicts fire ignition probability, fire spread, flashover occurrence, structural collapse risk. AI agents. Autonomous AI agents can monitor fire conditions, trigger simulations, analyze results, recommend actions, coordinate evacuation. Digital twins and cloud-based fire management. Digital twins represent virtual replicas of physical facilities. Components include physical asset plus sensors plus cloud data center plus CFD plus AI plus decision support applications, smart buildings, smart campuses, hospitals, airports, factories, data centers. Digital twins enable continuous risk assessment, predictive maintenance, scenario analysis, emergency preparedness. Security considerations. Fire simulation data may contain highly sensitive information. Examples: building layouts, critical infrastructure designs, security systems, industrial process. Data security is therefore essential. Major security risks. Cyber attacks. Examples: ransomware, data theft, denial of service attacks. Intellectual property theft. CFD models often represent significant commercial value. Data sovereignty risks. Data stored overseas may violate regulations. Security solutions. Encryption, AES 256 encryption, end-to-end encryption. Zero trust architecture. Every user and device is continuously authenticated. Identity and access management, multi-factor authentication, role-based access control. Quantum-safe security. Future systems should implement post-quantum cryptography, quantum key distribution. Secure virtual private networks. Encrypted communication channels protect data transmission. Costs of using third-party data centers. Costs vary considerably. Capital expenditure savings. Organizations avoid purchasing HPC clusters, servers, storage systems, cooling infrastructure. Typical local HPC investment: $1 million Australian dollars, 20 million. Cloud operational costs. Typical pricing components. Compute charges AUD 0.10 to 20 per CPU hour. GPU charges AUD 2 to 50 per GPU hour. Storage charges AUD 20 to 100 per terabyte per month. Data transfer charges 5 Australian cents minus 0.20 per gigabyte. Large fire simulation projects may cost 5,000 Australian dollars minus 100,000 plus depending on complexity. However, costs remain substantially lower than owning equivalent infrastructure. Business benefits: reduced capital costs, no need for in-house supercomputers. Scalability: resources expand on demand. Faster project delivery. Parallel computing significantly reduces simulation time. Improved decision-making. Real-time analytics support emergency response. Global collaboration. Researchers and consultants can collaborate internationally. Increased innovation. Organizations can rapidly test new fire protection strategies. Competitive advantage. Firms offering cloud-enabled digital fire engineering services gain substantial market advantages. Real-life applications. Example 1. Airport fire safety. Large international airports utilize cloud-based CFD to model smoke movement and evacuation strategies. Example 2. Metro tunnel safety. Underground transportation systems use cloud HPC for tunnel fire simulations and emergency planning. Example 3. Oil and gas industry. Major energy companies perform explosion and fire risk assessments using cloud HPC environments. Example 4. Smart buildings. Modern smart buildings increasingly deploy digital twins integrated with CFD and AI for continuous fire risk monitoring. Example 5. Wildfire prediction. Government agencies use cloud computing and CFD to forecast wildfire spread and support emergency management. Emerging technologies and future directions. Future fire management systems will increasingly employ AI-assisted CFD, AI agents, quantum computing, quantum machine learning, edge computing, digital twins, autonomous fire robots, augmented reality, virtual reality, federated learning, 6G communication networks. Quantum computing may eventually solve highly complex fire simulations exponentially faster than classical systems. AI agents may autonomously manage entire fire safety ecosystems. Consultancy, research, and business opportunities. Significant opportunities exist for consulting firms, fire engineering consulting, digital transformation consulting, risk assessment consulting software companies, cloud CFD platforms, AI fire analytics, digital twin solutions universities, collaborative research, industry-funded projects, professional training programs technology companies, HPC services, cybersecurity solutions, IoT systems startups, AI fire prediction platforms, autonomous emergency systems, smart evacuation technologies. Conclusion: third-party data centers are transforming computational fluid dynamics-based fire modeling and management. By combining cloud computing, HPC, AI, digital twins, IoT, and advanced analytics, organizations can perform highly detailed fire simulations, conduct real-time risk assessments, improve emergency response, and enhance safety while significantly reducing capital costs. The convergence of CFD, cloud data centers, AI, and emerging technologies represents one of the most important transformations in modern fire engineering. Organizations that adopt these technologies early will gain substantial advantages in safety, operational efficiency, resilience, innovation, and business competitiveness. The future of fire engineering is digital, intelligent, cloud-enabled, and increasingly autonomous. If you enjoyed this discussion, don't forget to subscribe, like, and share. Stay tuned for more insights on AI, quantum computing, and emerging technologies shaping the future of software and humanity.